In this chapter and in this section, we're going to start looking at antiderivatives. We're going to start thinking about antiderivatives graphically and numerically, and then we'll start introducing the indefinite integral in a later section. So in this section, we're going to try to understand the graphical relationship between a function and its antiderivative, and that's going to be very similar to what we did with a function and its derivative. In fact, we're just going to go backwards in that process. We're going to try to visualize antiderivatives using slopes. Again, that's going backwards to this process we did in chapter 2. And we're going to compute values of antiderivatives using the fundamental theorem, something that we've already explored in the last section. So first, let's start with the definition of antiderivative. If the derivative of f is f prime, then we say that f is an antiderivative of f prime. It is going backwards through the derivative process. So to get familiar with this idea, even though it's going to be something we're going to do more in section 6.2, let's start again thinking about antiderivatives of these functions, something we've been trying to build up to in the last few sections. So example 1, find antiderivatives of 2x. So that is, we are trying to find a function whose derivative is 2x. And one should maybe come to mind, and that is, what about x squared? And x squared is an antiderivative of 2x. However, it is not the only one. So this is an antiderivative, but it's not the only one. So whenever we talk about antiderivatives, we're going to be talking about more than one function. So for instance, another antiderivative is x squared plus 1. Because if you take the derivative of x squared plus 1, you get 2x plus 0, which is 2x. So that's another function whose derivative is 2x. You could also do something like x squared minus 7 halves. That's also an antiderivative. So there are some antiderivatives of 2x. Let's do a similar kind of thing this time with cosine. Find, in this case, all antiderivatives of cosine. We know there's going to be more than one. We kind of already showed that above in example 1. We're going to try to see how can we represent all antiderivatives. So first, let's recognize that the derivative of sine is positive cosine. And that means that sine is an antiderivative of cosine. We're using derivative rules to find antiderivatives. So this also means that sine of x plus 3 is an antiderivative of cosine, because the derivative of sine of x plus 3 is also cosine. And we could say, what about sine of x minus pi over 4? That is also an antiderivative of cosine. And what we can really say is, bringing it all together, is if we have sine of x plus c, that is an antiderivative for any constant c. So there's two things I want to make clear, a few things I want to make clear in this page. One is, this is looking forward to what we're going to do in 6.2, really introducing antiderivatives with functions themselves. But we can kind of already have an idea of, we have to go backwards to the derivative process. We need to think about derivatives to understand antiderivatives. And there are more than one antiderivative for one function. In fact, there are infinitely many antiderivatives for one function. We're going to have to use that fact in everything we talk about for the rest of this video. All right, so now moving on to thinking about antiderivatives graphically. Here's an example. We're given the graph of f prime below. That is, we're given the graph of the derivative. And we want to sketch the graph of the function given that f of 0 equals 1. And we'll talk about what this f of 0 equals 1 means in a little bit. But first, let's just think about if we're given the derivative, how do we think about the function? We're going to use the relationship that when the derivative is positive, right, we know that when the derivative is positive, that means f is increasing. And when the derivative is negative, that means that f is decreasing. So let's think about, when is this derivative positive? And positive means that we are above the x-axis. So this derivative is positive on the interval 0 to 4. It is above the x-axis from 0 to 4. So that means that f is increasing on the interval 0 to 4. Then we have that f prime is less than 0 on the interval 4 to, let's say, infinity. We're going to keep on going past. We're going to say this goes down to infinity. That means that f is decreasing on that interval. And we'll also have one more piece, and that is that we know that f prime is equal to 1 on the interval 0 to 2 on that flat bit. Right? So that means that f is going to be a line with a slope of 1 on the interval 0 to 2. And I think just with those pieces in mind, maybe one more thing, and that is at x equals 4, the derivative is 0, so that means that we have a horizontal tangent line at that point. And I think with all that information, we can graph the derivative with one more piece of information that we need, and that is that f of 0 equals 1. And we'll make this clear in a little bit, but without that piece of information, there are infinitely many graphs that we could draw that satisfy those criteria. But if we say that f of 0 has to be equal to 1, that means we have this point in the lower left-hand corner at 0, sorry, not 0, 0, 0, 1, but in that lower left corner. If we're going to start there, then we can kind of graph this thing. So let's start with the fact that f prime equals 1 on the interval 0 to 2. We said that means that f is a line with a slope of 1 on 0 to 2. So f is going to be increasing, slope of 1 on that interval. Then f is going to change. It's no longer going to be a line. It's going to be something curvy. But it is going to be, and actually we could say even more here too. We could say that f prime is decreasing on the interval 2 to infinity. It's going down on that interval. And that means that f double prime is less than 0, which means that f is concave down on that interval. So that gives us more information about what this graph looks like. All right, so here we go. We're going to have a horizontal tangent line at 4. This is going to be concave down, maybe something like this. We have a horizontal tangent line at x equals 4. It's concave down on the interval 2 to 4. There is a special point here at 2 where we go from a straight line to a concave down kind of thing. But there is a picture of our function f of x. So note that if we didn't have that criteria f of 0 equals 1, we could have drawn something like this, and that would have also been a function f of x. This might have been with the criteria that f of 0 equals -1 or something, where we start at a different point. And if we don't have a starting point, we could draw any kind of graph, just doing a vertical shift, really up and down from that original graph f. All right, so using the same example now, so given the graph of f prime below, and note that f of 0 equals 1, as we said, find f of 2 and f of 4, and we'll redraw the graph that we just had one more time. Or at least something close to it. All right, so there's our graph of f of x. We're going to try to find f of 2 and f of 4. So note that f of 2, we could just use the graph itself of f and find out that that's equal to 3. But we can also use the original derivative to find that information. And we could be thinking about the area under the curve from 0 to 2. So we know that the area under the curve, so under f prime on 0 to 2, that's going to be equal to the integral from 0 to 2 of f prime. And we know that's going to be equal to f of 2 minus f of 0. That's by the fundamental theorem of calculus. So this area is a rectangle. It's 2 units by 1 unit there. That's just going to be an area of 2. This length is just 1. So it's going to be an area of 2 is equal to f of 2, which we're trying to find, even though we know it's going to be 3, minus f of 0, which we know is 1. And now we can verify that f of 2 is indeed 3. So two different ways to go about that problem. One using the graph, the other one using the fundamental theorem of calculus. To find f of 4, however, though, I think we're going to need to use the graph, or sorry, need to use the derivative, not the function, because we don't really have an exact value of what that it's going to be at 4. But we can think about the area under the curve from 0 to 4. This area here is going to be a triangle. It's 1/2 the base, which is 2, times the height, which is 1. That's an area of 1. So we know that the area under f prime on 0 to 4 is going to be the integral from 0 to 4 f prime of x dx is going to be equal to f of 4 minus f of 0. This area is equal to 2 plus 1. We're looking for f of 4, and f of 0 equals 1. This means that f of 4 is going to be 4. So actually that means our picture is a little bit off. We should have that f of 4 is 4, that it actually goes exactly at that point and then goes down. So we're using the fundamental theorem of calculus, we're using the derivative and areas like we've done in previous sections. We can also think about the actual function itself, which now we know how to draw from the derivative. All right, let's look at another example here. This is thinking about the first and the second derivative test, given the derivative, not necessarily the function itself. So below is the graph of the derivative. We are going to find and classify the local extrema of f, the original function. So note that we have local extrema occur at So to find the local extrema of f, we know that occurs at critical points of f, and that are the points where the derivative is 0 or the derivative does not exist. So we know that the derivative is 0 here at x equals 1 and x equals 3. And that's not necessarily means that those are local extrema, but that means that if there are local extrema, they have to occur at those points. Remember, local extrema of the function, not of the derivative. The first derivative test says that if we look at x equals 0, the derivative is positive before, sorry, x equals 1 is derivative, or the derivative is positive before x equals 1 and then negative after, above the x-axis and then below the x-axis. So we have at x equals 1, f prime is positive before and negative after. And that means that we have a local maximum at x equals 1. We can do the same thing with x equals 3. Here we have the derivative is negative before, positive after. So derivative is negative before, positive after. And that means that we have a local min at x equals 3. We could use the second derivative test as well. Should give us the exact same answer, but let's double check it. Second derivative test says that at x equals 1, the second derivative is negative. That's because the derivative is decreasing at that point. And that would mean that we have a local max at that point. That matches what we have. And at x equals 3, the derivative is positive, and that's because f prime is increasing at that point. And that would mean that we have a local min, and that matches what we found before. Lastly, wanted to point out that we know that we have an inflection point at x equals 2 because the derivative is, the derivative of the derivative, the second derivative, is 0 at x equals 2. And we can say that f changes concavity at that point. So really what we're doing in this section is a lot of what we did in chapter 2. We're just going backwards through everything that we kind of did in chapter 2. Instead of giving the function and finding stuff about the derivative, we're given the derivative and we can say something about the original function using all the same kind of things and all the same relationships that we used before. In the next video, we're going to do some more practice problems relating to these relationships and looking at the antiderivative graphically a little bit more.